Hello everyone, today I'm going to be talking about the Advent of Code 2020, Day 7. Today we are looking at bags, shiny gold bags, light red bags, etc. And the first part of the problem is to find out the number of different types of bags which can contain a shiny gold bag. The data we are given looks at something like this. Light red bags contain 1 bright white bag and 2 muted yellow bags. Dark orange bags contain 3 bright white bags and 4 muted yellow bags. The first thing to realize is that this is a graph problem. So these are vertices, and light red to bright white, light red to muted yellow. These are edges. Okay, so here I've written up all of the vertices and all of the edges, and I have this very cool interactive graph that I can move around like so. Okay, so you can see that shiny gold, for example, can have dark olive bags or vibrant plum bags, etc. And the types of bags which can have shiny gold are bright white, which can directly have it, muted yellow, and then light red can have muted yellow, so it can have shiny gold. Now, when you're traversing the graph, the two main ways to do it are breadth first search and depth first search. For part one, it doesn't really matter which one we choose, but the point is, if you start, your starting node is shiny gold, and you traverse the graph, you're going to get to vibrant plum and dotted black, but you're never going to get to some of these other nodes. So the key to realize is that what if we were to reverse the graph? What if we change the directions of all of these arrows? And then shiny gold will point to muted yellow and bright white, and then if we just go through the reversed graph, which I have here, we will actually, if we just visit every single node in this graph, the number of nodes that we visit minus 1, like minus our starting node, will be the number of bags which can contain shiny gold. If you missed this part, you can always just rewatch this part of the video. This is an important detail. Okay, so first of all, I'm going to build the graph. So we get some data like this. And let's first get rid of all of the periods at the end of the sentences. And let's replace the plural word bags with bag. And then we're going to go for each line in our data. We are going to remove the white space from that line. And then, so we're getting rid of this white space here. Okay. Then, if this line has data, which it will have data, but then we're going to split the line at the word contain. Okay, I think it's always contain, never contains. Okay, so when you split it, this will be the first part, so it will be like light red bag, because we replaced the S with bag. And so when you split it, you'll have light red bag, and then this two things. And then you'll have dark orange bag, and this. So now we have our vertex. It's just that first part, like light red bag. This is our vertex. And then we're going to parse the neighbors. So if no other bag is in the temp neighbors, which is an array at this point, so the first element would be like this, and the second element would be this. So if one of the elements is like no other bag, then that means that there are no neighbors, so it's empty. And otherwise, we need to determine what all of the neighbors are. So we're gonna split the neighbor. Oh, so this will actually create the array. Okay, before it was just the string. And so now it's going to be like element 1, element 2. Okay. And let's remove the white space for the current neighbor. Okay. And the reason we have to split it into the individual words is because we need to know this number is number 1. And then, so now we've split it into like this word, this word, this word, this word. So we're going to join these words back together, and then we're going to store this count somewhere. Okay, so the count is like the first word, and then the value will be the joined words, like so. Like we have to rejoin these 3 words, so we'll have like bright white bag, and the weight will be like 1. We could actually make this in here. Okay. I didn't do that, but you know, you could do that. And so now we're going to append the weight and the value, which will be, the value will be like bright white bag or something like that. Okay. So now we have processed this vertex, such as light red, and we have all of the neighbors and all of their counts. Great. So we have our graph. So now that we have our graph, we need to so we could either, like I mentioned, we can either do a breadth first search or a depth first search, but I'm going to use breadth first search. So if you're not familiar with the breadth first search algorithm, you might need to look it up, but basically it uses a queue. So I'm going to do like the iterative breadth first search. You could also do it recursively, but I think the iterative is pretty easy to understand. So okay, so we are going to go through each of the neighbors for this, like each of the edges for this vertex. And by the way, this graph, as I mentioned when we're doing this breadth first search, we have to do it on the reversed graph. I explained why earlier in the video. So this graph is actually the reversed graph. All right, that is an important detail. So neighbor of value will be the actual name of the node, and then we can use like neighbor of weight to get the weight. We actually don't use the weights in part 1, so I'm just going to use neighbor of value. So this is just like some basic breadth first search thing. Okay, so you keep track of which nodes you visited, so you don't visit them twice. And then when you're done, we're going to return the visited. And sorry, so let me move this into a function actually. Okay, so it's kind of like a breadth first search, except at the end, we're not really searching for anything, we're just kind of like traversing the whole thing, and then at the end we're going to return everything we visited. So for part 1, you just need to build the graph, which I created a function for. Oh, and then we need to reverse the graph. So I didn't show how to do that, so let's create a function for actually reverse the graph. So the reversed graph, let's call it our graph, will have all of the same vertices. So let's create a dictionary which has all of the same vertices. So for each vertex in the original graph, vertex and the neighbors of that vertex, like the edges, sorry, this should be graph.items. Then we're going to do for neighbor in neighbors. So the value will be neighbor of value, and the weight will be neighbor of weight. And then we are going to, so you can think of it this way. If you have like a graph, and the original key was key and the value was value, now we're doing value and key. That's what we're doing. So now the value becomes the key, and the key, which was vertex, becomes our value. Okay. This is probably also pretty common knowledge, how to reverse a graph. Okay, so So we have the graph, we have the reversed graph, then we are going to do our BFS on our graph using shiny gold bag. This will give us our visited, and then we return the length of visited, but -1 because we don't want to include shiny gold. Okay, that's part 1. So part 2 is asking to find the number of bags inside the shiny gold bag. Okay, so for this part, we are going to traverse. Okay, yes, I have some talking points. All right, so let's go back to the original graph, like not the reversed graph. And what is our strategy going to be? So we look at, like, let's say we start from shiny gold in the original order, and you see shiny gold has vibrant plum. Okay. And so how many vibrant plum? Actually, shiny gold has 2 vibrant plum. Okay, so that is already 2 bags. And since we're going to do a breadth first search for this part, we are going to add the vibrant plum to our queue. And then, because we're doing breadth first, the next one we will process will be the dark olive. And then we have 1 dark olive, so we can add 1 bag to our total number of bags, and then we will add that to the queue. And then we need to go through the children of vibrant plum, which is kind of depth 2. So vibrant plum has dotted black. Now with a normal breadth first search, you would only visit dotted black once, actually, but we want to visit dotted black once for every single parent it has. So actually, unlike a regular breadth first search, where you would just like do shiny gold and then you would visit dotted black and then you would never add it to your queue again, we're actually going to add it to the queue every time for each of its parents. So when we add, okay, so first of all, how many bags is there for dotted black? So we know vibrant plum is 2 bags, and dotted black, let me look. Dotted black is 6. Vibrant plum has 6 dotted black. Okay, so there's going to be 2 vibrant plum times by 6 dotted black. That is 12. Okay, plus our original 2 from the vibrant plum. Okay, and all right, so now we have the dotted black, and when we add dotted black to the queue, we should add it with this 12 number. That would be useful to know. And okay, so I've written it down here in detail. So we add vibrant plum to the queue. Then we add dark olive to the queue. So vibrant plum has 5 faded blue, 6 dotted black. So we add faded blue. Oh, then we go through the, so we processed vibrant plum, then we process dark olive. Now we're going to process in this order faded blue and a dotted black. Okay, so we know that faded blue, the multiplier is going to be whatever the multiplier was of its parent, and times the number of faded blue, which is 5. And then when we process dotted black, its multiplier will be the multiplier of its parent, which was 1 times 2 times 6. So this is the idea. If it's a little hard to understand, I hope you can just rewatch this part and it will make more sense. Yeah, part 2 is a little tricky. Okay, so first of all, we're going to build the graph. We don't need to reverse the graph this time. So we're going to get the, I'm going to get the child count. We're kind of counting from assuming shiny gold is our top. How many total bags are there inside of it? So like how many children are there? Very good. And so we need to implement this BFS return child count thing. So the first thing is that we don't have visited. No visited. As I mentioned, we actually want to process the children like once for each parent. So this is the first kind of modification. And in the original part, we only kept the value. Now we need to keep the value and the weight. So I'm going to still keep source, but I'm also going to keep the weight. Okay. And this weight will actually be the cumulative weight, as I was describing. So rather than just storing the weight, we're going to store like 1 times 2 times 5, 1 times 2, right? It's not just the weight. The initial weight is 1. So very good. So this will be shiny gold when we first get into this loop. Then we're going to go through each of the neighbors of shiny gold. So shiny gold has like, what does shiny gold have? It has vibrant plum and dark olive. Alright, so this is going to be like vibrant plum or dark olive. And with a weight, so vibrant plum, it has like 2 vibrant plum, okay. Okay. Now if I'd casted this to an int before, you wouldn't need to do it now. But anyway. So we have the cumulative weight, which is it weight, and we have the current weight, which is like neighbor weight. Okay. So we're going to append to our cube. Like we normally would do with breadth for search, you add the neighbor to your cube, except here we're not checking if we've already added it, we just add it every time. And so this is an important detail. We're adding the cumulative weight, which is this weight here. We're not just adding the neighbor weight, we're adding like the cumulative product. Actually, this is the entire thing. So I'm just going to add a comment. Children will be added to queue once for each parent. And we're actually done. And sorry, I do need to keep track of this child count here. Okay, so that's it. And so we can just actually return child count. So that's it for day 7. Thanks for watching.